Thanks very much for this introduction. What is really amazing is I can skip forward to my introduction, like make it much faster. It's going to be fast-paced, only 20 minutes. So I work at Enclos right now, and for those who don't know Enclos, it's a US-based curtain wall company. We fabricate and install curtain walls, and we serve only the US market. You might have seen those precedent project by Enclos, the transportation hub with Santiago Calatrava in New York City. So our team installed all the glass panels and this operable skylight, which is at the top of this building. You may also recognize the SF MoMA, San Francisco Museum of Modern Art in San Francisco, which consists in this FRP freeform facade in front of a really typical curtain wall in collaboration with Chrysler's, of course. And Via 57 in New York City, this really iconic high-power building by big, like 500,000 square feet, including like window wall, but also this doubly curved stainless steel facade. So that's Enclos. So I'm steering our Los Angeles, specialty work, our advanced technology studio. And today, though, I'll talk to you about that research on ultra-thin glass and how to prototype with it. So yesterday we had some very interesting sessions on cold bend glass. Cold bend glass isn't new to our industry, right? It's been used in projects for over a decade. A cold bend glass consists in elastically deforming the glass. You all know that the Young modulus of glass is the same as aluminum, so it's actually quite flexible. It has been used in several projects, and to name a few, you got the Avignon railway station in France, called Ben IGUs. You have the ISC headquarters by Gary in New York City, also called Ben IGUs. And you have the Strasbourg railway station, collaboration RFR and our friends at Zilla. And further on that railway station, it's not just cold bending of the glass, elastically bending of the glass. It's also what we call so-called warm bending. People also call it laminate bending, which consists in stacking, I got a pointer, right? Stacking glass and interlayers, put them into a vacuum bag, clamping into a jig, and put that jig into an autoclave and laminate those things together. And what's happening then is when you take it out, the bound between the interlayer and the glass, the shear at this interface, prevents the glass from coming back flat again. So it still has this spring back. It wants to, become back flat again. But that's the presence of the interlayer that keeps that together. And so at the time at RFR in France in 2010 and 11, I did some extensive research in cold bend glass, studying various laminates, compositions, trying to understand how that shear, basically how that creeps in time. But another thing that I realized at the time is the stiffer the compound or the thicker the glass, the bigger the force you have. So which means that if you want to lower the force on your supporting structure or minimize the spring back, well, then you should go for thinner glass. And this is what led me to actually stumble upon this ultra-thin glass product. So I was told to not give any names in my presentation. However, it's not written, I can tell it. It's this Corning glass product, Willow Glass. It's called Willow Glass because it's produced in this draw fusion production method. You got molten glass in that gutter which overflows, and that's where actually the Willow Glass form and name takes place. It's then stretched and rolled into spools that go up to 300 meters in length and 1.2 meter wide. So imagine it, for a designer, 300 meters, that sounds unfathomable. That's like virtually infinite length of material. And it comes in variable thicknesses. Here we'll talk only about 0.1 millimeter, 100 micron, and 0.2 millimeters. You can have it thinner, you can have it thicker. We won't talk about too much beyond those two boundaries. It's used for semiconductors, electrical wafers. It's also used, Michel is using it for his solar panels. You have it for interior application as a scratch-resistant surface for walls. You can have it for also if you want to go into flexible electronics, but we don't want to talk too much about it. And so fast forward, got some funding at Arup 3 years ago when I was working there in New York, and a fellowship with an art organization in Brooklyn, Urban Glass, which allowed me to develop an engineer nerd kind of sculpture, which would use cold bend glass and this ultra thin glass together into the sculpture project. So the concept here is something I try to reuse in further research, so I'll describe this briefly, but if you want more information, you can go into my paper of 2 years ago. So basically the main two key points about it, its stiffness is derived from its corrugated shape. So you see this assembly of the glass elements in this corrugated shape actually provides inherent stiffness to the sculpture ultimately. And the second point is that it's a reciprocal system, which means that it's a closed system, and the glass elements are actually supporting each other or bending each other into space. So you don't really need to tie it down to a structure like the railway station. You don't really need to have all those forces externally to this specific sculpture. I thought it was a very strong. It was an intent for the artist that I am. And so this is just a little model, laser-cutted plastic, and then taped together. So that's the initial intent. And then through various rounds of value engineering and just value engineering, we came down from 18 pieces to 6 unique pieces. And you see here the fabrication stages. So the glass, I procured the glass through Corning subcontractors Core 6 base in Virginia. It came in this banana shape, flat shape. And then here you see where I'm assembling one glass panel onto a V-shaped sweep, which is 3D printed, and that really joins the glass pieces together. And it's assembled with means of clear VHP tapes, double-sided. And so here was the first dual assembly, and each couple, there's 3 couple of them, are connected onto each other through that kind of a spiral geometry. And so this is how it looks. It's so transparent that you actually can't really see it, but that's basically 6 pieces. This is the sweeping V rotating up, and because it's so impossible to actually look at the time, I invited Michael Ludwig, who 2 years ago was the chair of that session, to. We were both in New York. He touched it. We broke some glass, and then the day after, we were on a plane to Finland. And then that sculpture stayed in my storage in Bushwick in New York City, and I derived a couple of lessons when I opened this my storage after a couple months in the summer of New York. So first lesson was the bonding method or bonding material that I used, the clear VHP tape. I had chosen this over epoxy, for instance, for immediate bonding. That was very important. The epoxy I tested with, especially in the summer in New York City, had extremely long curing time, so that was not appropriate to my cold bend structure, which wants to flatten back again. So I needed to have immediate bonding, and it's also quite flexible. So throughout the stages of construction of the structure, I did need some rotation at the joint. That's why the VHP tape was really a good solution at the time. However, through the summer, time and temperature crept, and the creep of that material, the glass starting to flap out and peel out. And so, of course, the capacity of VHP tape in long-term load is not really the best thing, but I think if you keep in mind the flexibility and the rotation capacity, the immediate bonding, these are things that I think should be kept for the development of that system. And then secondly, there's 3 lessons. Secondly, the glass started to peel off, but actually just for that specific geometry, specific loads, and size of panels. What I should have done at the time is just, when you want it to not start peeling, we just arrest the beginning of the peeling so that it doesn't peel off. So what I should have done would be to have started with this kind of tape that prevents it from starting peeling, and that would just have been sufficient. And the last one is, you can see here, the glass broke along the edges of those sweeping V's. And what happened there is, I used 3D printers that were limited in size, so my entire sweeping pieces were actually composed of 3 sub-assembly parts. And we're at the location where I brought those together, actually the stiffness, I had a discontinuity of stiffness, and basically that created a hinge around which the glass broke, basically. So having continuity of stiffness is going to be important. So with those lessons in mind, I hoped that many architects, many students, universities would be coming up with new design and keep evolving that research. A few roadblocks would be, not everybody can buy those fancy laser cutters that Corning is selling to you for a couple $1,000s. You can ask Michelle. Or not everybody can, purchase, but also wait for subcontractors like Corsix to cut the glass for themselves. You need to find a method that you can cut and prototype everywhere, anywhere, and let people play with it. That technique is actually quite different. This is scrub and break. So basically, you do a score in the glass, like the tile in your bathroom, right? You score it and you break it on your knee. That's exactly the same concept. You create a vent, a score, and you mechanically detach it. And the score is created by this diamond wheel. It costs a couple $100. It's procured from Japan. The waiting time is enormous. So not every student or every university can purchase it. So I was looking for means of fabricating, of cutting the glass with a purchase that you can find in universities or any architecture practice, such as laser cutter. So I did some research with laser cutting. And to do that, we leverage an opportunity we have at Enclos to have a residency at the Autodesk build space in Boston. That space is kind of a dream for an structural nerd, because it's a space filled with cooker robots, plasma cutter, welding station, tube bender, 3D printers, just name it. That means that for prototyping, this is excellent. We can just do and test. We also test water jet. And so to give you an idea, this is what the space looks like. And so we're just welcome to use our residency and this opportunity to go prototyping with it. So not only does it have machinery, but it also have the convergence of so many startups and designers that can combine their ideas. And our neighbors, actually, I'm jumping the gun here, but I wanted to talk about the context of Boston. Our neighbors were developing a product, a hologram product, which needed to be laminated, actually plastified like those library cards that you have. I don't know if you still have this anymore, but this kind of little cards. They used the exact same concept to plastify their hologram system. And that's actually at room temperature. You use a press. It's this very heavy steel press, not coated, but with a surface that's kind of rubbery. And basically how you do it is we wanted to do a laminate with 2 sheets of glass and an interlayer. It happened to be a PET film interlayer. And so what you do is you put your glass onto a substrate, which can be or shouldn't be paper in our case. This is how we did it the first time. So you put your glass substrate, and then you got this PET film that's coated on both sides with an adhesive. You peel a protective layer, and just as it approaches your press, you just peel off the protective coating, and then through the press, the interlayer is going to be bound into the first sheet of glass, and you do the same for the second. This is how we got a room temperature laminate. we did a lot of experiment with those, but to really, for benefit of time, I'm going to talk to you about one, which is a bending test that we did on some of those samples. I'm going to show you also the post-breakage behavior of this little mini sample, 100 mil by 20. So on the I'm going to show a video. What you'll see is basically the first, bend state of the laminate, and then we'll see that we have 2 inches that form on the compression side, about a mid-height, mid-span. And then when the tension side broke, this is when it was a complete failure of the laminate. However, the interior kept the pieces together, which was quite interesting. And that's the video. So you see also how much you can bend this material. You got a first hinge here, you got a second hinge there, and then this is the tension surface breakage. But we didn't expect to have this order of breakage, but this is how it happened. And if you want to close up, this is how that thing broke. So I told you earlier, or I should have told you, that this product has the behavior or breakage pattern of annealed glass. So it breaks in large shards, at least at the aspect ratio, like quite large shards. And you can see how much the interior returned the glass. So there was very limited pieces of glass that flew off. And what you can see on the right and left side is probably a misalignment of our laminates, but ultimately it was quite satisfactory. And because we had water jet available, we did also a couple of stupid things. But this is the nature of exploration, the things that, there's not so much data available, or you can, when you're exploring for prototyping solutions. So what we did is we used that water jet that's available at the Boston Build Space. It comes with this water and this Australian red sand aggregate that's used for cutting thicker pieces of glass. It was just a bad idea. This is a laminate that you see here, and these are the samples that we got from it. So extremely bad edge condition. It's actually what you're looking at. It's completely fractured glass, just held together by the interlayer. It's pointless, but we had a lot of fun with it, so don't do it. Next is we try to, back to what I was initially talking to you about, played with the laser cutter available at the Boston Build Space, playing with parameters of the laser cutter, namely the intensity of the laser, the speed as well, and different backing materials. And this is what you're looking at right now. So no backing was not extremely satisfactory. The edge condition was just not very good. The steel backing was not either satisfactory. You see how the edge condition is really bad. And what happened is the steel mirrored the laser basically back up, and this dual flow of the laser, which was just not appropriate for that thickness of the glass. And the best result was, that video on the right, which we won't see. Plastic backing and MDF backing gave the adequate absorption of the heat of the laser and gave us the best results. 2 things to point. Laser is actually not a continuous flow. I just didn't think about it, but if your laser is actually moving too fast, you'll have this kind of dash behavior because the light is not following at the same speed. So you'd see that. So you should know how to use a pointer. You shouldn't go too fast. Another thing to be noted is the focal point of our laser didn't match the top surface of the glass, probably because of some backing surfaces thickness, and resulted in cutting those very interesting stripes of glass where you'd have like a left side and right side of the laser. So that resulted in this phenomenon which we had to account into our fabrication process. And then we submitted those samples to bending. So we had 14 samples, not so much, but this is what we had. The number 9 didn't make it. It was just dropped before we got to bending. This is before bending and after bending. And we got 4 samples of laser cuts. So these are on the left-hand side. You can see how before testing, the short edge condition was not very good. However, the specimens didn't break at those locations, so it was satisfactory breakage, and we used those for the study. We also realized that they were not doing very well, so we decided to manually sand 3 of them. So 1, 2, 3, 4. Those the 3 were sanded on the edge and see if the amelioration of the edge condition would enhance the capacity of those samples. And then we had 2 that those 2 should be those 2, that we produced with the actual diamond wheel that we ended up purchasing for a couple $100, around $500, just to manually, diamond wheel cut those things by ourselves, handmade. And then our index were the samples here on the right, which were produced by Core 6, again, the subcontractor from working with Corning products, and they were our index, because the goal was to say, all right, if what we have available is done by them, how can we approach those results? And we do have a little bending video that shows the apparatus, extremely professional apparatus that I had to come out to just bend those things. But so I made sure there was no metal to glass contact. And you can see how I'm moving the support of that bend strip together, close to one another. And you can see at the scale how much you can flex it. And most of the breakage happened at midspan. Of course, I had safety goggles. So this is what we done for all the tested pieces, which were, as I told you, like 4 types: laser cutted, sanded laser cutted, hand cutted with scribe with this diamond wheel, which you can do like any shape of vent. And then our index on the right side. And basically what you're saying is the laser cut samples didn't perform very well in the average of like 40, 50%. And that was just enough for us to say, well, have fun if you want, but the capacity of those samples, this methodology is really not very promising. And this is about a conference like sharing lesson learned, so just don't do that. And so it's probably worth buying this Japan-made wheel in order to move forward. So the next steps in that research were hooking this up to an XY, like RZ router that we can use to cut the glass. So that's what will be done forward. And in the next 2 minutes, I'm gonna tell you more about this USC, University of Southern California, students that did a thesis. When you don't have time to work on this thing, you just have a student working for you. So she did an excellent job as an architect, developing a very good, thorough documentation of what has been done so far with ultra-thin glass. And she developed her own pavilion concept. She was very keen on using tensile structure language and system, which derive a little bit from my first research, but she was interested into that. And so, to keep it short, developed some very interesting connection system. And to just name one, she transposed a few, rigging detailing that you can see, again, like in membrane tensile structures. So for instance, this one was very interesting. She came up with that. It's basically a shoe in which you insert the edge of the glass, and then that shoe itself has some holes, and she decided to weave this along one of the cables. So that was quite interesting. She also learned about all the technology for prototyping. So how do you print on, 3D printer volumes that it's just 10-inch cubes, so that's quite limited. How do you assemble them together? And then, so she made this mock-up with plastic. It's not glass. And then she assembled that with a hot glue gun, basically, to the 3D printed sweeps. And she also had like a little truss element. And then she built it. We put it in our studio. demonstrating the viability of our structural system. Did a couple pictures, and this is at the studio if you want to come see us in Los Angeles. And yeah, took a couple of pictures of it. And this is it. I hope you enjoyed this presentation. I will welcome any questions.
Hi there. Did you like what you just saw? If you did, why not like the video? Drop us a comment below, as well as share the video with others, since GPD is all about sharing. And to receive more videos in future, subscribe and don't forget to click the bell icon for notifications. Ciao.